Hello. Can people hear me? Please let me know. Perfect. All right. Good. So today we continue momentum, and an exciting topic, and well, it can be very tricky. So I'm going to go through 7 quite tricky problems with you today. And one of them is going to be almost exactly the same as problem number 12, I think. Well, the last problem anyways, the last problem on the assignment, which is with 2 stars. Yeah, the difficult one with this sandbag. Right. Okay. Here we are. By the way, can you tell me how many problems from physics have you managed to do so far? 8. Good. Ooh, impressive. Okay. All right, yeah, so that's fine. Hasn't started the physics. Okay, so today mostly we'll be talking about impulse. Impulse is the change in momentum, right? So impulse is the change in momentum, and it's also equal to the force times delta t. Right, so problem 1. An object is stationary on a rough horizontal surface. A horizontal force F is applied for the object for delta t seconds. Find the friction force if the object stops after 3 delta t seconds after beginning of motion. Okay, so what are we up to? We have a force, horizontal force, F, applied to the object for delta t seconds. And then it starts accelerating. And at some point, the force disappears and the object starts to decelerate because of friction. Okay, and it's stationary again. So of course there's a friction force acting throughout. Let's call it F friction. And this is FA, applied force. Okay, well, let's just call it F. Applied force is F. Okay, so here we can look at it like this. There is an object, the force is giving it momentum, and the friction is taking the momentum away. Yeah, so the force is giving it momentum and the friction is taking the momentum away. So how much momentum does the force give? F delta t, yes, F delta t. And what's the impulse of friction? Well, it's going to be F friction delta T, 3 delta T. Okay. And since these are the only two forces, and we start with total, and we know that total impulse must be 0. Yes, because we start with 0 momentum, we end with 0 momentum. So initially, change in momentum is 0 overall. Therefore, F delta T plus, well, minus F friction, because friction is in the opposite direction, 3 delta T must be 0. Delta T cancels, and we get F friction equals 1/3 F. Okay. And that's an interesting way of looking at a force. The force gives you momentum and or takes away. A force changes momentum. Yes, ultimately force changes momentum. Okay. Does this question make sense to you? On a scale of 1 to 10, please. Okay, good to see. Good to see a lot of 10s. So this will be the main theme of today's session. Yes, impulse is F delta T. We're going to use it a lot today. Right. Problem 2. A spaceship has momentum P. It needs to change direction by alpha degrees, keeping the magnitude of momentum the same. Okay, so basically keeping the speed the same. So basically a spaceship wants to turn, let's say, for simplicity, well, without we say, so as scientists say, without loss of generality. Okay, we can say that the spaceship is turning right. So the spaceship is traveling horizontally, and then it's turning right at a small angle alpha. And it has momentum P, P1, or Pi, and P final. And we know that P initial equals to P final by modulus. Okay. The force is, the engines can produce a force F. So which way should they be pointing? And for how long? Perpendicular to what? Perpendicular to the initial velocity. Okay. Let's say there's a force F. Which acts for a time delta t. So the final momentum is going to be the initial momentum plus the change in momentum. And change in momentum, we know that it's force times delta t. So P initial plus force delta t. Let's have a look what happens. So this is the initial momentum plus force delta t P initial of delta t. What do we see? What can you tell me about the final momentum in this scenario? Ooh, Alfie, very good. Alfie. It has to be slightly backwards. Indeed. Very good. Yes. So in this scenario, the one that you suggested initially, Alistair, your final momentum is going to be bigger because you are adding this bit. So the force cannot be perpendicular. The force has to be at an angle. The force has to be something like that in order for, so the picture would look like this. This would be the same, and this is going to be like this. And this would be an isosceles triangle. Right, it's an isosceles triangle. You could say, oh no, it's not. It's not perpendicular. No, this is an isosceles triangle. So we know that this is alpha, and therefore we know that these are the same. So these are pi over 2. No, pi minus alpha over 2. Pi minus alpha over 2. And this is pi minus alpha over 2. Okay. So yes. So according from this diagram, maybe I should redraw it. Well, that should be fine. Therefore, so I'll do it again, sorry. So there's the initial momentum. This is the initial momentum. This is the final momentum. And this is the difference between the two. This is delta P. Delta P, which is equal to a force delta T. And this is P initial, P final. This angle is alpha. Therefore, this angle is pi minus alpha over 2. And this is also pi minus alpha over 2. So using the cosine rule, we can find delta P. Delta P squared is equal to Pi squared plus Pf squared minus 2 Pi Pf cos alpha. So delta P squared is equal to Pi, which is P squared. So it's 2P squared minus 2P squared cos alpha. And we know that, so delta P is equal to P multiplied by square root of 2 minus 2 cos alpha. And delta P is F delta T. F delta T is equal to P square root of 2 minus 2 cos alpha. Therefore, delta T is equal to P divided by F multiplied by square root of 2 minus 2 cos alpha. That's the time. And then we need to find the angle at which the force must be applied. And the angle must be like this. And this angle, if this is pi minus alpha over 2, then this angle is, I'll label it with green. This angle is alpha over 2. So the answer, alpha over 2 to vertical. Okay, so that's that. What else? Well, also you could say, well, if you can manage to put a force which is always perpendicular to the motion. In this case, this becomes circular motion. Alternatively, force always perpendicular to motion. Force always perpendicular to motion, and motion. Therefore, we have circular motion. The motion with constant speed. Okay. Now, what else? What happens? Why this can be complicated? Oh, because your rocket is pointing a certain way, and you can say, right, I would like the rocket to fire, I don't know, northwest. And you can turn the rocket northwest and fire the rocket. Now, fire the rocket perpendicular to its motion is not an obvious task if you think about it, because you're in space. You can't. It's not like an airplane which stabilizes itself along the air, the movement in which is along the with the air. There's no air in space to stabilize the rocket, so the rocket can travel. So the angle of the direction of the rocket has nothing to do with the actual direction of motion. Yes, so the rocket is pointing that way, it might as well moving sideways. Okay, there's no, you can't really make a detector that would, you can't always tell which way is the rocket is moving. If you're inside the rocket, you definitely can't feel it. Okay, so this is one way, but this is very difficult. This is difficult. Here you can say, point the rocket towards that little star and shoot it, and shoot shoot and fire it up, and that makes more sense. In this scenario, because the force is that way. The force is that way. First, the rocket slows down a little bit because the force is against the motion. So the rocket slows down here. Slows down. Because force is down and left. Slows down. Down. And here, it speeds up again along this path, because now the force, there's a component, there's a vertical component of speed, so we are increasing the vertical component. So here it speeds up. Speeds up. So these are two different scenarios. Yes, so it depends on how the rocket is made. Yeah, perhaps some rockets can do that, but I think the easier way is that. Okay, I hope I haven't confused you here. Do you understand? You understand this problem? On a scale of 1 to 10, please. Okay. This is maybe a bit confusing with the yeah. So it's an alpha over 2 to your no, it's pi over 2 minus alpha over 2 to your initial direction, if you think about it. Okay, problem 3. This is the difficult problem. This is the problem of problems, which doesn't seem that hard until you do it incorrectly. So most people will do it incorrectly. So this is the same problem as the bag of sand that is thrown out of the window. And I'll show you the most popular incorrect solution of this problem. So we have a box with sand of mass m on a rough horizontal table, friction coefficient mu. A bullet of mass m hits the box with speed v at an angle alpha. The bullet quickly stops in the sand. For how long will the sandbox continue to slide? Right. And for what angle alpha will the box not move at all? So you should have reacted to the double star in the question, in the original question with the sand bag of sand, because it's not as easy as it seems. So I'll show you the incorrect solution first. Correct solution. Okay, can somebody help me with the incorrect solution? If we kick the box and the box starts sliding, are we trying to go and try? We could do. But can you help me? As in, can you talk me through the solution? Because the solution that you have in your head is probably the incorrect one. I'm sorry to say. So use conservation of momentum. So what's the momentum of the box? Momentum of the box after momentum of box after collision. Collision. well, that's what is the momentum of the box after the collision? Or velocity of the box after the collision? So can you apply conservation of momentum, please, to the bullet and box? You can talk to me. I would be happy to discuss.
So obviously you add the masses.
Sorry?
You add the masses, obviously, in the second part.
Well, yes. So m plus m times u, yeah?
Yeah.
Times u. That's the velocity of the box after. So once the bullet is inside, the box will move along, will slide along the table. So this is before and after. Before, after. It moves with velocity u. Okay. I'm using u because that's the initial velocity for the box after once the collision has happened. Okay. So the momentum after the collision is equal to the initial horizontal momentum. Yes. mv. Come on, help me out here. The total momentum of the system before collision is equal to the total momentum of the system after the collision. We're talking about horizontal momentum. The total horizontal momentum before is equal to the horizontal momentum after.
So what's the velocity of the bullet again?
V.
Is it v? So
Yeah.
v cos alpha.
Yeah, V cos alpha. V cos alpha. All right. And then you find u. So velocity of the box is equal to mv cos alpha divided by m plus m. Okay. And now you use suvat because the only force acting on the box, is friction. After the collision. So we have the box. The box is moving. Box and the thing moving. The initial velocity is u. And there's a friction force which is equal to mu n, mu mg. Okay. Well, not mu mg. It's going to be mu m plus m g. Therefore, you have Newton's second law, Newton 2, have mass acceleration is equal to the resultant force. So m plus m acceleration is equal to the force, which is minus mu m plus m g. You can cancel the m plus m, so acceleration is equal to minus mu g. And then, is this a constant acceleration? It is, so we can use that. The displacement we don't know, we don't care. Initial velocity is given, is mv cos alpha divided by m plus m. Final velocity is 0, the box stops, acceleration is minus mu g, and t is equal to question mark. So we use the formula v equals u plus at. We're looking for t, so t is v minus u divided by acceleration. So we sub that in z0 minus mv cos alpha divided by m plus m over a minus mu g. So that's going to be mv cos alpha divided by mu g m plus m. Right, and that's the time for the box to stop. Time for the box, time to stop. To stop after collision. And the first question, how does this solution contradict the question? How does this solution contradict the question? I'm not sure if you see the question, but so this is the time to stop. This is the time to stop. And this is the question. So where is the contradiction? Tell me, please. Maybe not a strict contradiction, but it contradicts the spirit of the question. I love this phrase. Contradicts the spirit of the question. Sounds nonsensical. Right. Don't be shy. Come on, it's a difficult question. Yeah, it doesn't really show for which angle the box doesn't move. So at 90 degrees, well, yeah, if you shoot at 90 degrees, the box won't move. Yes, you're shooting vertically upwards. But it suggests that for any angle other than 90, the box would move. This answer suggests that the box would move regardless of the angle, everything except 90 degrees, which kind of doesn't make sense. It seems like there should be an angle for which the box moves. Again, I can easily imagine some like hitting a box with, I don't know, with a bat and the box not moving.
Is it because the friction isn't always mu m plus mg?
Well done. Yes, exactly. So this solution is wrong because solution is wrong. Is wrong. Wrong because friction is not constant. So why is it not constant? Was that Alistair or?
Yeah, because the frictional force is less than or equal to mu m plus mg. So as it slows down, it will be less and less and less till it stops, isn't it?
No, no. As long as it is sliding, the friction is that. Now, the issue here is that when the bullet hits the box, it pushes the box into the ground. As the bullet hits the box.
So the normal reaction is different.
Yes, it pushes the box into the ground. This is called a dynamic force. Dynamic force. Or shock force. Dynamic force. Then the friction, the normal reaction increases. Friction increases. Okay. Now you have to understand this question is the first year university style question, and it's a difficult first year university style question. Friction, normal reaction increases, friction increases. Okay, so let's look at the correct solution. So let's define something. So delta t time the bullet to stop. So basically, so what's going on as it hits the let's say this is the moment the bullet hits the box. The friction force increases dramatically and then decreases. This is the friction force. This is time. So the friction delta t. The delta t, this is the time when the bullet stops. So this is a very short time, but this increase in friction can be quite dramatic. And this this area is the impulse delivered by friction. Okay, it's the impulse that is taken away from the box. So I'll just time. And let's call it delta t plus delta t. Okay, let's put it this way. So this is delta t. Delta t is sliding, and this is the bullet hitting the box. The bullet bullet decelerating, in box. Okay, time for bullet to stop. Delta T, time for box to stop sliding. Okay. So what we can say impulse delivered by the impulse delivered by F, well, by the bullet is I equals F times delta T. Yeah, we need to draw a free body diagram. Body diagram on the box. So when the bullet hits the box, there's a force like this. This is the force of the bullet on the box. And there's a friction force, mu n. There's a normal reaction force, n, and mg, of course. Mg. Okay. And the impulse delivered by the bullet, so we can assume that the bullet is traveling much faster than the box will slide. So the impulse is equal to mv. Yes, mass times the initial velocity of the bullet. And therefore, the force is equal to mv over delta t. This is the force from the bullet. Okay, so now we have the vertical forces. Vertical forces. That is the normal reaction must equal to mg plus f sine alpha. Okay, so the vertical forces are balanced because it is not moving up and down. Therefore, the forces are balanced. Horizontal force. So yes, that's the vertical forces. The impulse. Horizontal impulse. Horizontal impulse from, well, we can, so yes, the horizontal impulse is equal to horizontal impulse from friction is equal to, so this is minus mu, and then the minus mu n, that's the force, times delta t, which is minus mu, open bracket, mg delta t. Well, okay, delta t, mg delta t, plus f sine alpha, f sine alpha y sine. Oh yes, f sine alpha. Yes, and delta t. Delta t. Okay, and here, because the time is very short, so because the force is many times bigger than mg, yes, the force with which the bullet hits the dynamic force with which it acts for a very short time is large compared to mg, we can neglect this term. So basically, the friction doesn't change the momentum during the time the bullet stops. So the horizontal the horizontal impulse from friction is that. So the final momentum of the box is equal to the impulse delivered by the bullet minus the impulse delivered by the friction. The impulse from the bullet is mv cos alpha. That's the horizontal momentum. Okay, mv cos alpha minus the friction, which is mu f sine alpha delta t. And f, we already know, it's mv delta t. So that's mv cos alpha minus mu mv sine alpha. So this is the final, this is the momentum of the box. Momentum of the box after collision. Momentum of box. So once the box is moving, once the box is moving, with the bullet, it will friction will deliver an impulse to stop the box. How does that work? The force of friction. Is there any? No questions so far. All right. The force of friction multiplied by delta t. That's the time it takes for the box to stop. Is equal to mv cos alpha minus mu mv sine alpha. And from here, we know that the friction force is equal to m plus m M plus M mu M plus M G delta T, and we can work out that delta T set delta T is equal to fraction, and it's going to be this over G. Right, and that's the time. So it's quite different. Well, quite different-ish from this. So it's actually MV cos alpha minus that. So this answer does not take into account the increase in friction, and this one does. And what happens if delta T is 0 if MV cos alpha minus mu MV sine alpha is equal to 0. Therefore, cos alpha was cos alpha. I'll write it with a pen. Cos alpha minus mu sine alpha equals 0. Cos alpha equals mu sine alpha, mu alpha tan alpha is equal to 1 over mu. So if alpha is equal to arctan 1 over mu. So if alpha is greater or equal than arctan over 1 over mu, then the box won't move. Okay. So you can use this. You can use this solution to solve the problem 12. I hopefully that makes sense. I'm afraid to ask, but how much sense does this problem make to you personally? On a scale of 1 to 10, please.
I'll just say that it feels kind of weird to leave out the mass of the box in its final momentum.
We're not
Right.
weaving out the mass of the box. We are saying that the momentum delivered by the friction during that short time while during the short time that the bullet is stopping inside the box, we say that the friction doesn't really do anything. The friction due to the mass of the box, if that makes sense.
So that's assuming that the mass of the box is quite small then.
We're talking about a dynamic force. So we're talking of a bullet of significant size that is enough to move a heavy box. So it's either the box is light or the bullet is heavy, or the bullet is traveling at a very high speed. And if the bullet is traveling at a very high speed, the force would be enormous. Yeah, like you can put a book on top of an egg, the egg won't break. But if you smash an egg against an egg, it will break, because the force can be what 50, 60 times bigger when you smash it. Okay. So when you throw a bag of sand out of a window onto the pavement, you have to assume that the force with which it hits the ground is many, many, many times more than if it was just lying there. Does that make sense?
Yes.
Okay. So yeah, so we have to assume that. And the same with the sand. With sand, you just with the bag of sand, you throw it, and the dynamic force, the hit, is so much greater than the actual weight of the bag. Okay. So, oh, I love these. Okay, so I try to go quickly through those. A glass container of negligible mass is on an absolutely smooth table. The container is filled with liquid of density ρ and volume V, 0. A beetle of volume V and density ρ starts to crawl along the bottom with speed u relative to the container. Find the speed of the container. Right. So why would the container move in the first place?
Because the center of mass needs to stay the same and the beetle's moving and there's only internal forces involved.
Yeah, absolutely. The center of mass must be constant. Or you can argue that, well, because in order to move, there has to be a friction force forwards on the bug, and therefore there's an equal and opposite force on the tank. So the tank will move left and the bug will move right. Oop, that's not what I meant. Okay. So there's an interesting approach we can say here. So we compare the tank with the bug inside and the tank without the bug. So the bug, the beetle compared to liquid has mass, has extra mass, which is equal to rho, V multiplied by rho minus rho 0, times, oh yeah, that's it. The beetle compared, yes, this is the extra mass. So imagine the beetle was, instead of a beetle, we have the same amount of liquid. Yeah. Now it's a beetle. It's just a beetle is just basically a slightly more denser liquid. And we have to assume the beetle is more dense than the liquid, otherwise it would float. So it's on the ground, so therefore it is not. That would be a very interesting thing if the beetle was lighter than water. Then when it attempted to move forward, the tank must move backwards, which is really cool if you think about it. But anyways, the extra mass of the beetle. So we can assume that it's just a tank. So mass of tank, therefore, mass of tank is going to be V plus V0 are rho 0. Okay. Mass of tank, mass of beetle. Beetle is V rho minus rho 0. Okay. Does that make sense? So we are what do we mean by tank? By tank, we mean if it was filled with liquid and the place where the beta is was also filled with liquid. And when we say mass of beetle, we mean the extra mass of the beetle due to it being heavier than wood, more dense than wood. So we have mass of tank, mass of beetle, and therefore we can use the we can find the momentum of the beetle. Momentum. Is it moving with a fixed speed? Ah, yes, momentum of the beetle. Momentum of beetle. Beetle is V rho minus rho 0. Multiplied by U. So the beetle is moving with, oh, it's relative to the container. All right, so the beetle is moving with velocity U, and this is moving with velocity, let's say moving with velocity V. So the beetle is moving, the momentum of the beetle is U minus V. Momentum of tank must be the mass of the tank, so V plus V0 multiplied by rho 0 multiplied by V, minus V. And they must add to 0. Why U minus V? Because the beetle is crawling with relative to the container. So relative to the ground, it's U minus V. Does that make sense? Momentum of beetle relative to the ground, relative to table. To table. And this is relative to table. The tank is moving left. Yeah, Andre, does that make sense? It's moving left. We just say that this is positive. This is the positive direction, and we can say it's minus V. It's a matter of choice how you approach this problem. So therefore, the total momentum must be 0. Momentum is V rho minus rho 0, U minus V minus V plus V0, rho 0 V, and that must be 0. Therefore, V rho 0 V plus V0 minus plus V rho minus rho 0 is equal to U V rho minus rho 0. So apologies, I'll just skim through that. This is does something cancel here? V rho 0, v rho 0 cancels, and we have v, so the speed of the tank is equal to u v rho minus rho 0 divided by rho 0 v 0 plus rho v, and that's the speed of the tank. Okay. And interestingly, if the density of the bug is less than the density of the liquid, V, as you can see here, V is going to be negative. So the tank is going to be moving backwards. And that's that's very disturbing if you think about it. Very disturbing, because the bug is moving right. That means it's pushing itself right. And if it's pushing itself right, the tank must be moving left. And yet that is not the case. If the beetle is lighter than the water, and it's somehow managing to cling on the ground by some bizarre method, like I don't know, very sharp claws, and it's holding to the bottom, preventing it from floating, and it's crawling right, the tank would the tank would move in the
So how would that work? Because surely the center of mass would change then.
yeah, because when the bug is moving right, the center of mass shifts to the left. Therefore, the tank has to also move to the right. Oh, that doesn't make sense, does it? When you say it out loud, it doesn't make any sense.
Or wait,
Yeah.
so the density is less to the right and it's greater to the left. So the tank must move to the right.
A second. Less density. There's less density on the left. So there's a negative, basically there's a negative mass moving to the. Yeah, I think I've tricked myself here, because
So wait,
yeah,
if
go
you,
ahead.
if you consider the density of the water 0,
Okay.
and the density of the beetle is less than that, then that's a
Yeah.
negative density relative to the water tank.
Yeah.
So when the beetle moves to the right, the center of mass moves to the left. So the tank has to move to the right. Is that right?
Yeah. It does sound right. But when you consider that if the beetle moves to the right and the tank moves to the right, you have a movement of the center of mass, don't you?
Yeah.
Right. I'll have to look into this. If you have an answer to this, that would be great. Yeah. Don't don't take me on this. So we found the speed, and that's fine. Okay, I'll just double check that it is correct. And check that it is correct. Rho minus rho 0 VU rho 0 V. Yeah. Yeah. So if the density of the beetle is less,
But I mean, if the beetle's lighter, then it would just float upwards, so it couldn't.
Yeah,
push
but
the-
if it managed to cling onto the ground by means of a sharp claws, for example.
So there's got to be some mechanism stopping the beetle from moving to the right or something. Stopping the tank, the whole tank beetle system from moving to the right.
Well, yeah, no. Actually, I think it does make sense. If the density of the beetle is less than the density of the water, moving the beetle to the right will cause the tank to move to the right as well. Okay. Right. We don't have. So this is an interesting question. Nuclei decays into 3 particles of mass m1, m2, m3, traveling at usually perpendicular velocities. V1, V2, V3. Mutually perpendicular, so this means in 3D, find the speed of the nucleus before decay. So we have mass of a nucleus, and it decays into 3 perpendicular pieces. All right, two, 3 pieces that travel perpendicular to each other. Find the speed before decay. Well, we have initially m1 plus m2 plus m3 plus m3. And we know that the velocity, let's say u, so m1 plus m2 plus m3 multiplied by u, by the vector u, is equal to m1 v1 plus m2 v2 plus m3 v3. So v1, v2, v3. Okay. And we can find that u, the speed of the nucleus before is m1 v1 plus m2 v2 plus m3 v3 divided by m1 plus m2 plus m3. But because these are mutually perpendicular, because m1 v1, so let's say m1 and v1, so this is m1 v1, this is m2 v2, the total vector is going to be m1 squared v1 squared plus m2 squared v2 squared. So Pythagoras theorem. And with 3, it also works. So this is going to be square root of m1 squared v1 squared plus m2 squared v2 squared plus m3 squared v3 squared. So using the fact that they are mutually perpendicular, we have this m2 plus m3. Okay. So basically, if vector A is perpendicular to vector B, then modulus of A plus B is equal to the square root of A squared plus B squared. That's important. And if A is perpendicular to B, perpendicular to C, and C is perpendicular to A, I don't know if you can write it like this. Well, if they are mutually perpendicular, A, B, and C, A, B, and C are mutually perpendicular, mutually perpendicular, then A plus B plus C, the modulus of A plus B plus C is equal to square root of A squared plus B squared plus C squared. Therefore, you can use that. So the sum of 3 vectors which are mutually perpendicular is this. Okay. Let's quickly skim through that. Problem 6. This is a what if question. Well, not a what if, but a paradox question. Imagine a horizontal treadmill with no friction in the rollers or axles. A person attempts to walk forward. Person attempts to walk forwards. Since the total momentum of rollers and thread is 0, the person seems to be unable to change the momentum of the thread and rollers. Okay. What do you think about this question? Yes, there is. If you take the thread and rollers, the person applies an external force. But the rollers have a total momentum of 0. So the rollers are staying still. The rollers, they are rolling, of course, but the total momentum is 0. Momentum of rollers is 0. And the thread also, because some of the thread is moving right, but the same amount of thread is moving left. Why are my rollers going that way? They should be going the other way. So the thread is not powered, yeah? If it's not powered, but there's no friction. So some of the thread is moving left, but equal mass is moving right. So the momentum of the thread is 0.
Wait, so by no friction, the axles aren't actually affecting the tread?
No, they are. It's there's no friction in the axles. Means that there's no friction here. Nothing is slowing them down.
Okay.
So look, if you look at the thread, half of the thread is moving left, half of the thread is moving right. So the total momentum is 0, right? The rollers, I mean, the top of the roller is moving left, the bottom of the roller is moving up, so the total momentum is 0. So no matter how fast the rollers are rolling, and no matter how fast the thread is running, the total momentum is 0. So now you put a person into the system. So if the person cannot change the momentum of the rollers and thread, that means the person must be stationary. Because if the person suddenly starts to move, with velocity v, that means momentum is not conserved. And that doesn't make sense. That's a paradox. That is a contradiction. So how can we resolve this contradiction?
So the person doesn't change position though, doesn't he? But he is
Well,
moving.
that is the question. can the person change position? So if you're on a treadmill with no friction, if you attempt to walk forwards, will you stand still?
Wait, what? If you attempt to walk forwards, will you stand still?
On a treadmill.
So the tread won't move if you try to move forwards, or something.
That's the question. So, horizontal treadmill, no friction. The person attempts to walk forward. So you want to walk forwards. Your aim is to get to the end of it. This is your flag, and this is your aim. So you want to get here. Okay. And by looking at these two facts, it seems that you won't be able to do it. It seems that you won't be standing still, and no matter how fast you run, you won't be stationary. It's just the rollers will be spinning under you, and that's it. Does the question make sense?
So that's the answer. You won't move.
Well, I don't know. Does it agree with your experience?
I can't remember the last time I usually run outside. I feel like if you ran fast enough, you could overcome it at like a certain setting, surely.
Yeah, or otherwise you can say, well, you're using friction, right? So you're pushing the thread backwards. That means it has to be pushing you forwards. If you're pushing it back, that means it must be pushing you forwards. And if it's pushing you forwards and that's the only force on you, you must be walking forwards. But then how do we resolve the contradiction that the total momentum is still zero? Okay, advanced question.
You're moving backwards.
Yeah.
You're
Sorry?
Wait, so you're being pushed backwards.
No, you're
Just
pushing the thread backwards. You're pushing the thread with your feet backwards. In order to walk forward, you have to push back, right?
right. But so is it on? Is it moving like by itself?
No, it's there's no friction and it's not connected to a motor.
So I'll say you won't move.
But you are pushing it backwards. You're applying a force. That means it must be applying a force on you forwards.
You're moving relative to the tread, but not to the ground, surely.
But if you're pushing the thread backwards, right? The thread must be pushing you forwards, Newton's third law. Your feet are pushing the thread backwards. Feet are pushing thread backwards. The thread, this causes the thread to start spinning, or start moving. But because it is half of it is moving left and half of it is moving right, the total momentum is zero. But this means the thread is pushing you forwards, pushing your feet forwards. But that's how you walk on any terrain. When you run outside, as you do, you push the ground back and the ground pushes you forward. Okay, well, I'll resolve the paradox. And so what we haven't considered is that when you try to walk forward, you push the whole system backwards. You push the thread backwards. And this causes a force in the axles. There's a normal reaction force in the axles that will push the rollers forwards, and that's your external force. The axles will push rollers forwards. This force will be transferred. This force is then transferred to your feet. Transferred to your feet. Your feet. So you won't stay still. You won't stand still. Right. Make sense? The external force. So you can only be moved by an external force, and the external force is the normal reaction in the axles. And ultimately, it's the ground pushing you forwards. Okay. I have another question. Well, I don't have time to do it, but see if you can do it on your own. The answer is NMG. And it's a really fun thing to do. Answer NMG. NMG. Well, or NM. I mean, if you're reading on the scales, it's NM because it gives you in grams. Right. Okay. So yeah, let's stop here. And I hope you all have access to the board. Right. Okay, so have a lovely evening and have a lovely half term. I'll see you next week. Welcome.